We've been talking about different ways to make amines. If we have a secondary amine, we can react with an acid chloride, and then we now have 3 carbon groups bonded to that nitrogen. Lithium aluminum hydride reduces it to a tertiary amine. So we might call this acylation reduction, converts a secondary amine to a tertiary amine, and we get rid of the amide with a lithium aluminum hydride. So before I get to this slide, I typically like to talk about, it was in an earlier slide, say I want to make an amine like this. And so I go, okay, I'm going to get alkyl halide, but your book will tell you this is a stronger base than this. And so before too long, you can get multiple alkylations. So one of the previous slides showed if you use an excess ammonia, you can kind of tone that down, getting multi-alkylations. So not really the best synthetic way to make a primary amine. So I like to say somebody came up with an angelic method, some guy with the last name of Gabriel, where they kind of lock down the nitrogen in this thing called a phthalimide ion. Then we have a primary alkyl halide. And here's our friend hydrazine. Kind of looks like a luminol. Man, if you had the ammonia group there, you'd have a luminol, wouldn't you? But anyway, and that kicks this out, and you get your primary amine without multi-alkylations. The phthalimide ion is a strong nucleophile, displacing the halide or tosylate ion from the alkyl halide. So we could also have a tosylate instead of the alkyl halide. SN2 fashion, we get our primary amine. After we heat the N-alkyl phthalimide with hydrazine, displaces the primary amine, and we get our product there. Any questions on the Gabriel synthesis? Other ways to maybe get a primary amine. Reduction of azides. Azides are kind of explosive. They're kind of reactive. Most airbags have an azide compound in them. They're stable enough to package up in an airbag, but you can get a bunch of N2 gas when needed. Here's what we want to do with the azide today. Acts as a nucleophile, so just an SN2 type reaction. And then lithium aluminum hydride. We reduce that azide into a primary amine. So negative charge on that, good nucleophile, and we can react this with unhindered secondary or primary halides or tosylates. Alkyl halides, the workhorse of many organic synthesis reactions. Alkyl azides are explosive, so reduction is carried out without purifying this. So if I said name all the compounds that you can think of that have nitrogen in them, like a nitro group, azide group. So here's a cyanide, and here's a nitrile. And so cyanide, you'll recall from chapters 7 and 8, a good nucleophile SN2 type reaction form the nitrile, and then you can reduce that to the amine. Just a little review question. What other things can you do with nitrile, like aqueous acid? What do you get? You can get a carboxylic acid out of it, and there might be some ways to stop at the aldehyde. I'm not sure. So the cyanide group, good strong nucleophile, works well in SN2 reactions. Then we can reduce the triple bond down and get an amine. So to convert an alkyl halide or alcohol via the tosylate to an amine, form the azide and reduce. To convert it to an amine with an additional carbon atom, form the nitrile and reduce. In either case, the alkyl group must be suitable for displacement. So let me just review what that might be telling us. Let's see, let's come up with something. So we got to think back to January. Our reaction of alcohols, let me change this here. So it's one way to form a bromide. That last little hint said we could form tosylate. This is just easier for me to write. And then this thing acts as a nucleophile. I'm trying to preserve my shapes here. There's kind of our symbol for reduction with the lithium aluminum hydride. So we have the same thing going on here. There's my Lewis structure of the cyanide. Still do our reduction. I'll just draw on lithium aluminum hydride. Now there's a little added twist in that our carbon chain gets one carbon longer. So we added that carbon. So we can make an alkyl halide into a amine by nucleophilic substitution with azide, reduce it. Or if we do the nitrile, we'll have an alky chain that's one carbon longer. So here's a nitro group. Here's a metal. Metals like to give up electrons. And so this is a suitable reducing agent. I think we can probably use lithium aluminum hydride. And in lab, when this was on a benzene ring, you use that sodium thiosulfite reagent. So if we can just replace 2 oxygens with 2 hydrogens, under these conditions it's protonated, so now we deprotonate it. So the nitro group can be reduced to the amine by catalytic hydrogenation or by an active metal under acidic conditions. I think there's even more reducing agents commonly used to synthesize anilines. What does that mean? Aniline. So also in the OChem lab, a lot of times we have students do this and they use iron and HCl gets the job done. So last week I said we're going to skip a little bit because I want you to see the diazonium salts as it relates to putting different groups on a benzene ring. So now we're going to look at this, conclude this chapter with this middle part. Amines as leaving groups. Amines can undergo elimination reactions to form alkenes. Notice this looks like that strong base we use in our acetylene chemistry. That would be an alkylated version of the same thing. Are not good leaving groups because they're super strong bases. Exhaustive methylation can convert the amino group into a quaternary ammonium salt, which can leave as the neutral amine. I'm kind of skeptical, and I know that if I put this in water, I'm going to get some hydroxide. So, you know, ammonia is a weak base, but we're not going to worry about that. Exhaustive methylation. So I just talked about the Gabriel synthesis and how when you have an alkyl halide and amine, it's hard to stop it from just putting one alkyl group on there. So we put on one, then we put on another one, and then we put on a third. So here's our ammonium salt. Once that's occurred, here's a base coming in there, pulls that off, those electrons jump down. This leaves. So there is the elimination, Hofmann elimination. So there should be a little asterisk here. Probably anhydrous conditions, but evidently nature does this. Heating the hydroxide salt produces the less substituted alkene. So the hydroxide salt, notice we have this silver oxide. It's probably where that oxygen came from. Notice there's some protons there. I don't think we have to worry a whole lot about the mechanism. So a poor leaving group. Now we have a good leaving group. And so here's some iodide left over. Methyl iodide is usually used as a methylating agent, and the leaving group is the neutral amine. So here's our quaternary ammonium iodide. We've just exhaustively methylated the ammonia, and I said somehow we got to get hydroxide. So now here we have our quaternary ammonium hydroxide. Silver iodide precipitates out. The iodide salt is converted to the hydroxide salt by treatment with silver oxide and water. The hydroxide will serve as the base in the elimination step. So we can see E2, it's concerted. You're like, man, I'm glad I got that down last fall, right? And there's our alkene. The Hofmann elimination is a one-step concerted E2 reaction in which the amino group, the amine is the leaving group. Regioselectivity. So when I look at this, I think I could put the double bond there or the double bond there, and Zeta swirl probably says put the double bond there. All right, so let's just go through the mechanism. This thing puts a bunch of methyl groups on there. This forms some hydroxide. Silver iodide is precipitated out. So yeah, we can pull off proton here and put the double bond, or we can pull off a proton there and put the double bond. So it's interesting. In the alkene chapter, the only way we could get the Hofmann product was with a bulky base. Otherwise, nature would give us this. What's going on here? It says the least substituted product is the major product of the reaction. And so we call it the Hofmann product. Now, can we come up with a rationale why that might be? This looks kind of bulky, so maybe it's a steric hindrance issue. And that's what it was when you'd use the T-butyl oxide on your alky halide and get the Hofmann product over the Azides product. So I'm gonna back up because we're gonna see why this is with the Newman projection. Here's C1, C2, C2, C3, and we see we form more of this one than the Azides product. So this all has to be in the same plane. Here we see it all in the same plane. Pull this off, and that's gonna give me my Azides, the more substituted alkene. Looking along the first two carbons, so maybe it's a statistical thing. It says any of the three staggered conformations is suitable for E2. So notice, this is the most stable configuration. So that's crowding there, you don't have here. So we can either have the methyl groups anti to each other, or we can have this bulky trimethyl nitrogen anti to one of the methyl groups. The key to solving Hofmann elimination problems is to find all possible ways the compound can eliminate. Then the one that gives the least substituted alkene is probably favored. All right, we've been reducing nitriles, amides, nitro groups, azide groups. What about oxidation? Now notice this is what you get when you react an amine with a ketone or aldehyde. And then we can reduce that to the mean. Here's an ammonium salt. Here's the hydroxylamine. Here's an amine oxide. Here's a nitrose group and nitro. Amines are easily oxidized even in air. Common oxidizing agents, hydrogen peroxide and MCPBA. Secondary amines oxidize to hydroxylamines. Tertiary amines oxidize to amine oxide. I should have got this. Benzoic acid. This is one of these per acids. I think there's another group on the benzene ring. Tertiary amines are oxidized to amine oxides, often in good yields. Either peroxide or peroxy acid may be used for this oxidation. The N-oxide can undergo elimination to form alkenes in a reaction analogous to the Hofmann elimination. Cope rearrangement. Notice we have our quaternary amine, which is kind of like a good leaving group. And here we see the hydrogen and this thing leaving in kind of almost a classic elimination type way. Here's the transition state, and here is the alkene. An E2 mechanism. The amine oxide acts as its own base through a cyclic transition state, so a strong base is not needed in the Cope rearrangement.